Hey, yo, let's discuss. Come on, Amos. You gotta get one, dude. Hey! Go. Well, I'm recording this, so let's go. There we go. For those in the video who are not in our class here, who are watching this, Amos just did a double backflip off the ground. It was incredible. Okay. Hey, listen. Today, don't worry about this. We did a different warm-up. We're going to talk about limits at infinity, which sounds super cool. Okay, I know, right? Your homework is on this document. Let's discuss Canvas, kids. Canvas has everything we do in class inside of it. Go to Canvas homepage, click on the day. That's what we've done. If you miss a day, go to Canvas and see what's happening. Don't email me. Don't say I didn't know. All right, I'm saying it's there. Go look. Cool? I'm putting videos on there so you can see. Like if you weren't here yesterday, I think most of you guys were here yesterday. But that was basically a day off. You could have kept up with us. You know what I mean? Come on now. Anyway, we're going to be talking about limits at infinity. And for the most part, guys, we're talking about right here, horizontal asymptotes and end behavior, okay? Yeah, all right. You should have seen horizontal asymptotes and end behavior before. Like, you all know the end behavior of like y equals x squared is like up, right? You can say it like that, right? Pop, like this. Okay? We're going to talk about, you ready? What y value is f of x approaching as x gets bigger and bigger? So as you plug in bigger and bigger and bigger values of x, what y value do we approach? There's a couple easy rules. These are not going to require a ton of algebra. I see we're on some cell phones. Excellent. I hope you're having a good time on there. Okay? If we take a look at this right here, this very first question, as x is going to infinity, 2x plus 1 over x, I'm hoping you saw somewhere along the lines that if the degree of the numerator is the same as the degree of the denominator, and you're asked what's the horizontal asymptote, which is what limit as x approaches infinity is asking you, that's a fancy way of saying what's the horizontal asymptote, then it's just the coefficients as a fraction. Okay with that? Okay? We'll talk about why that is in a second. Because I'd like you to actually think about this, not just memorize some rules. But if you had to memorize rules, I mean, whatever. You can also see on the graph, here's 2 right here, right? As x gets bigger and bigger and bigger, those y values approach 2. As x gets more and more negative, those y values approach 2. That's what we're saying. Easy enough? Okay? Now, let's discuss y. You ready? As x gets bigger and bigger and bigger, like if we plug in 100 kajillion, the top is going to become 200 kajillion plus 1. All right? That's like 2, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. That's what that is, okay? 200 kajillion, there you go. Over one of them. I made too many zeros, I regret this. But guess what that equals about, guys? 2. Very, very close to 2. Okay? So what's happening here, when you see limit x going to infinity, okay, and it's a fraction, what you're really looking at is how the top and the bottom play together, okay? Like they're fighting. The top wants to make it real big, right? And the bottom wants to make it really small, because as the denominator gets really large, it makes the fraction small, like 1 over 10, 1 over 100, 1 over 1,000, 1 over a million, right? It gets small, okay? But if they grow at the same rate, they just cancel each other out. That's what's going on there. So as x is getting bigger and bigger and bigger and bigger, all we really care about in that fraction is the 2x on top and the x on the bottom. All right, now, same thing happens over here. You ready? Blah, 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 blah. X goes to infinity. Here we are. 3x cubed minus 8x squared. All this junk doesn't matter. All right, if I put this down here, okay? As x goes to infinity, here's what I'm telling you. The x cubed term on top is going to become so big that the rest of this junk doesn't matter anymore. All right? Like it matters a little bit, but it just matters less and less and less as x gets bigger and bigger and bigger and bigger. Okay? And in the denominator, the x cubed term is going to get so big that the rest of the stuff down there no longer really matters. Okay? It's kind of negligible. You can think about it like that. So the 3x cubed and the 5x cubed is what this thing actually starts to look like. But that would reduce down to 3/5. Everybody okay with that? So, couple key things. We're having a quiz coming up here. I'm going to ask all the same kind of limits we've been seeing. Okay? I'm going to ask to find slope at a point, like we started the year off with, really, right? Like here's x squared, find the slope at 4. You do a little limit thing going on, okay? I'll give you a review. I hope that sounds somewhat familiar. I'm going to ask you to find the derivative using the definition of derivative. We're going to have piecewise functions and ask are they continuous or not. Okay? And then you're going to see limits like this. So when you see a limit x going to infinity, you switch off thinking, I have a bunch of algebra to do, and you start thinking, how are they going to play together? What's going to happen, all right? So we're just going to go through some examples. Any questions so far? 3/5 makes sense. Feeling good? Yes? I will later. I'll tell you. It's not till Monday, okay? Okay. If they are polynomials, and the degree of the denominator is greater than the degree of the numerator, then the denominator is going to get way bigger than the numerator. That's what happens. Denominator is real big, numerator stays relatively tiny. Can you see what's happening on the graph there? That's going to spit out numbers that are close to 0. In this case, the numerator is always 5, and the denominator is going to get bigger and bigger and bigger and bigger and bigger. Right? 5 over 100, 5 over a million, 5 over 100 billion. Yeah? That just becomes closer and closer to 0. Keeping in mind, it never ever hits 0. Ever. It just gets real close to it. How close? As close as we want to make it. The bigger I make x, the closer that gets to 0. That's what that says. Okay? Okay. Yeah, you might want to pay attention to this, kids. That's just me, whatever. I just want to explain this over and over again. But that's fine, you know, you need a minute to chill and search on your cell phone, whatever you're doing, that's cool. Okay. So hold on, we have degree of the numerator and denominator are the same, that's going to cancel out, right? You get the coefficient fraction there. If the degree of the denominator is larger, and I'm asking you as you go to infinity or negative infinity, that's just going to be 0. Which leaves us with the last case, that the degree of the numerator is larger, okay? And maybe you learned that there's no horizontal asymptote. That's fine, but I want to know which way the graph is going. So here's what we're saying. You ready? As x gets bigger and bigger and bigger, the only thing that matters in the numerator is x cubed. That's all the only things there. And as x gets bigger and bigger and bigger and bigger, the only thing that matters in the denominator is really x squared. All right? And do we know what x cubed over x squared is going to reduce to? Just x. So what that tells us is, so this graph does not look like x. It's got some other weird junk going on, okay? But when x is really big, it does behave like x behaves. It won't exactly be x, but it'll be linear. Do you see the end of that graph? What's it look like? It looks like a line. That happens to be called an oblique asymptote or a slant asymptote, if you want to think like that, but it doesn't really matter. I don't care what that line is. I just want you to know that it looks like a line. Can we handle that? Okay, because x cubed over x squared reduces that. And because we know that, without even looking at that graph, when you see this question, your thought process is, oh, that looks like this, x looks like that. As x gets bigger and bigger and bigger, this is going higher and higher and higher. That's going to infinity. Infinity, yep. What that says is this. The larger I make x, the larger the output is. I can make the output larger by making x larger. Greater, whatever. Yes? So even if there were a coefficient here, like 4x cubed, that's a good question. This would just kind of reduce down to that, right? It's still going to be a lot. Yeah, so to stretch it, right? So basically that's multiplying it by 4. That's going to stretch it. So make it a little bit steeper, but we just care where it's headed. Yeah? Yes? Good, good.
It's like what if it's an x cubed on the top and x on the bottom?
Okay, so if it's a different x's on top and bottom, we'll take a look at that in a second, okay? Good question, good question. Okay. The bottom question right here, as we hit a negative infinity, do we all understand that's asking about the left side of the graph? Right, the left end behavior, and because this graph looks like a line with a positive slope, like y equals x, then this is going to negative infinity. Easy enough. What's up?
Oh, no, I was just saying it's the only one where this end is different.
Well, yeah, so it just depends. So, yeah, I don't have any hard, like, fast rules for these, except for, like, if they have the same degree, then it's going to be the coefficients, right? We know that. But let's take a look at this one. Ready? Ho, ho, ho. Look at that. X is going to infinity, and we have x to the fourth over x squared. X to the fourth is going to win that fight. You with me? By a degree of 2, really. As x gets bigger and bigger and bigger and bigger, that's going to become close to this. And we all know that reduces down to, which means the ends of this graph should look like a parabola. And holy crap, look at that thing.
What would the frowny face?
Now, the middle, guys, what we're doing right here does not dictate anything about the middle. Okay? The middle can have all kinds of junk going on. That's not what we're saying. We're saying when x is very big, the only thing that really matters is the biggest thing on top and the biggest thing on bottom. That's what we're looking at. But only if you see x going to infinity. If x is going to any other number, do not do this. That's a totally different question. Yes?
Infinity and negative infinity, or just
And negative infinity also, yes, because that's on the left side. We feeling good?
yeah.
Okay? Yes.
Oh,
All right.
another example.
Oh, we got so many examples. You ready? Now this one's a little bit weird. When I throw a square root in there, y'all see the square roots? Yeah, okay.
Yeah, but
The rules still are kind of the same, because the square root of x squared, I know you all can think, is about x, right? It's actually the absolute value of x, but we'll talk about that in a second. All right? But that means this essentially, right here, is going to boil down to 4x over the absolute value of x, something like that. But only when x is big. Okay? When x is real big. But what's 4? So if x is really big positive, though, what's the absolute value of x going to be? Just positive, it's just x, right? And 4x over x is just 4. And look what happens when x is really big positive. Where's it headed? Right to 4. It has to. If you plug in big numbers, it's going to be real close to 4. Now, the reason why I bring this up, this example here, is because now when we're headed to negative infinity, though, it looks like it should still be 4, right? But a square root throws this little wrench in there. It does want to be 4, right? It's trying to be 4. It's like, I can be 4. I'm so close to 4. But
You're -4.
what kind of number is the numerator going to be? A negative number. Y'all see that? It's going to be a big negative number.
yeah.
But the denominator is going to be a big positive number. Y'all with me here? That can only happen with square roots. But that's why it is -4 on the left side and not +4. Okay? You can see that happening there, right? You also see, this is an instance of a graph going through its horizontal asymptote. Graphs can do that. I know teachers told you somewhere along the line that graphs can't go through their asymptotes. That's not true. Okay? All right, you feeling okay? You ready? We're going to play a game. Here it comes. It's called Check Out That Ass, Tote. That was funny. That's a math joke. I'm going to pause this, rewind it, and say that again, and you better laugh at my jokes. Oh my God. When you see that notation right there, folks, I'm saying what's the end behavior on the right side. Is that okay?
Yeah.
Okay. If you have something like this up here, over. Once I put that there, what do we know the answer is? 0. Okay? What if I put a negative infinity in there? Still 0. If they're the same, 3. Now? 4/5. Oh my. Boom. If we go to negative infinity, it's just?
Negative 4/5.
No, 4/5.
Positive.
It's positive, guys. So remember, I said square roots can do that. This can't. Look, what kind of number is the top going to be if I plug in a big negative? No, a big negative. It's going to be a big negative. But what's the bottom going to be? A big negative, which makes the whole number positive. That's why it's still 4/5. It's the square root that stops that from happening. We'll take a look at that in a second, okay? And here we go. Let's think. We're going to positive at infinity, and this here is an x to the 6th power.
Yes.
Let's think about that one.
It's gonna be x cubed.
It's going to look like x cubed at its ends, at the left and right side, not in the middle. Boom. But as I go to infinity, where's this headed? Infinity, yes. Woohoo. But as I approach negative infinity, because this side's down and this side's up, because it looks like a cubic at its ends. Easy enough?
I guess so.
Okay, good. You ready?
You're recording all this, right? So we can like go over.
I am recording this, yes.
Yeah.
Here we go. What about, oh, wait, don't yell it out. Let's think about that. Hold on. Think about it. It's a square root on that thing. What do you think, Danny?
I think it's infinity. I'm probably wrong.
Okay, so, it's a bad attitude to have, but you do happen to be wrong. Yeah, that's all right. I like your gusto, buddy. It's not infinity, because what's that square root going to turn that x to the 6th into, man? Square root slices it in half. It's a half power. What is this? This is 2/5.
Yeah, that's what I just said.
You did just say that, I know.
Yeah.
Do we see that? The top is in a square root. So that 4 is really a 2 over 5. Can we hit? Yes, maybe, sort of, kind of. Yes.
So the x to the 6th power would be x to the 3rd.
Because it's in the square root, yes. So hold on. Let's make sure, gang. Listen to me please carefully here. The top, this does not reduce to x cubed. Right? There's a plus and minus in there. Like, you cannot simplify that like that, okay?
Alright.
That's not what we're doing. What I'm saying is that when x is really, really, really big, the only thing that matters up there is the 4x to the 6th. Okay? Everything else kind of fades away. And that is going to be 2x cubed. But only when x is real big, which happens to be the question I'm asking you right this very second. Okay?
Yes.
Please be careful with your simplifications. You can't just cancel those things out. Why aren't you erasing? Great. Okay. Was there a hand up? Yes. Okay. Good question. What if this is 4x to the 5th? Who wins that fight? Numerator or denominator? The denominator wins. That's 0. Yeah, so essentially the numerator has a degree of like 5 halves. Even though it's got a lot of junk up there, that you can kind of think like that. As we're going to infinity. That's okay. It's got to be to infinity. Okay? All right. Hold on. Let's go back to 6. What if I'm going to negative infinity? Negative 2/5. Okay? Because the numerator will be positive while the denominator is negative. Okay? Okay. What up? What do you mean it's 1? And 1 in the denominator? Will that just be a linear, like this? That would just be that, dude. What's 2x plus 1 look like? The right side's going to infinity, okay? All right. Last one. You ready? If I put an 8 in here and a 4 in here, just to be careful.
Oh my god.
Check the top and bottom. So it definitely wants to be 2/5, right? So I'll rule for that. But the square root kind of adds a little bit of flavor to it. Both of those are going to be what kind of numbers, though? The numerator is going to be positive or negative? Positive, because you raise to the 8th power, and the denominator is going to be positive also. So the answer to this is positive 2/5. All right? Okay. Any more what ifs? So that's that. You can practice some now. The only other kind of asymptote you're going to be seeing is exponential. Okay? Well, I'll throw some other stuff at you here. We'll just start with exponential for a second. Do we all agree that if you plug in gigantic numbers, when you have 2 to a power, 2 to a gigantic number is a gigantic number, yeah?
Yeah.
And as x gets bigger and bigger and bigger, 2 to the x gets bigger and bigger and bigger. Without bound, we use the notion of infinity to discuss that. Okay? It heads to infinity, we say. As x goes to negative infinity, think about that. 2 to a very big negative number, a huge negative, is really 1 over 2 to a huge number. That's 1 divided by a huge number, that is 0.
Oh my god, yes, I got it right. I thought it was wrong.
Excellent. Now, look, just because we have a couple of these like this doesn't mean that's always going to be the answer, right? I can make all kinds of weird stuff up. So take a look at this one right here. Look at this thing. Woo! As 2 goes to infinity here, the exponent, as x goes to infinity, the exponent, which is negative x squared, is going to be what kind of number? It's going to be negative. Yeah, it's negative, think about it, negative 1,000 squared. That's 2 to a huge negative number, right? And it's going to keep getting bigger and bigger negative. So this is, and you see that happening. Look, where's this graph going? 0. Okay, but just because one side's 0 doesn't mean the other side's not 0. As I approach negative infinity, like negative a million, you're going to square it, which makes it positive, but then you're going to make it negative. So it's 2 to a huge negative number, and that's going to approach 0, which you see happening on the graph. Okay? All right. Let's get weird. If you see a trig function, don't freak out, guys. So this is more conceptually like you're thinking about what's happening rather than having a bunch of rules going on. Okay? If I ask you what's going on here as x goes to infinity, you're going to recognize, hopefully, that this is a weird exponential function with a trig thing up in there, sine. But as x goes to infinity, what's sine do? It bounces back and forth between what? No.
Oh, 0 and...
What's the biggest sine gets, folks? And the smallest? Sine bounces between 1 and negative 1. Which means 2 to the sine will bounce between 2 to the first, 2, and 2 to the negative 1, 1/2. You guys with me on that? 2 to the first is 2, to the negative first is a half. Look at this graph. It hits 2, then a half, and then 2 again, and then a half. So we do that forever. Okay? That's it. It's not like it's not equally distributed like that. You see how it kind of curves a little more in some places? Okay, that's because of the exponential, but that's okay. But as x gets bigger and bigger and bigger, this graph is going to do that forever. But it never approaches any number, which means this limit, since it doesn't approach anything, is dn. Oh, okay. All right. Let's try a couple weirdies. Ready? Yeah, a couple weirdos. Here we go. Yeah. We like the different. We like the weirdos. Absolutely. They add flavor to life. Absolutely. X is going to infinity. That's just a fraction. You're comparing the numerator to the denominator. The biggest thing in the numerator here, kids, just because you see sine, don't freak out, is sine of x. The biggest that gets is 1. The smallest it gets is negative 1, right? That's going to bounce back and forth. But x on the bottom is going to get bigger and bigger and bigger and bigger. So we have numbers that are between 1 and negative 1, being divided by numbers that are getting bigger and bigger and bigger and bigger. Where's that going? Going to 0. Okay? You don't have to think crazy for these. Look, this is what this graph looks like. It bounces because it's sine, but it bounces less and less and less because you're dividing it by x. Okay? Yeah.
I like that.
Cool? Yeah, it's nice. That'd be a nice tattoo there. Right up your arm. Spiral around it, that'd be good. Okay?
I should get it.
You get that? I should get that. What else? Here we go. Let's see who's thinking. Discuss these. So these, this is a little bit different. We're going to 0 here, but we can handle these. As I approach, you try to plug 0 and we get 1 over 0. True?
Yeah.
1 over 0. It is undefined, but that's not the answer to our limit. 1 over 0 means there's a vertical asymptote. Well, I'm only asking about the left-hand side. How do we check the left-hand side? We know it's 0. When you plug in -1, you get, where's the left side going? This answer is, as we approach 0 from the right for that function. And y'all have learned that before. Like 1 over x is a simple graph. It just does this. Yeah, you know what 1 over x looks like. Now, the reason why I'm asking that, you ready? Here's what I really want to ask. Okay, I'm going to be quiet for a second. I want you guys to think about this. There you go. Think about it. Think about it till you're so confident. Do it.
Confident like me, except you, right?
Okay, so look. As we approach 0 from the left, we're going to get 2. This goes to negative infinity. So we get 2 to the negative infinity, which is 1 over 2 to the infinity, essentially. And that's 1 over a gigantic number. So that's what a number, like a number greater than 1, raised to a huge negative, is going to approach 0. But what's weird, as we approach 0 from the right, where's that going? To positive infinity. Well, that's going to spit out 2 to the infinities, which is going to be a giant number. So look what this information tells us. It's kind of weird. Think about this graph. As I approach 0 from the left, so here I am from the left, where am I headed to? To 0. Y'all see it? You're headed to 0. That's what we just said. But there's no point there, because I put 0 in, that's an undefined idea. So it heads to, it's kind of got a hole right here, like that. It heads right to 0. But as I approach 0 from the right, it goes to infinity. So that's an example of a graph that has like a weird hole on the left and an asymptote on the right. Anyway, I hope that reasoning makes a little bit of sense. For homework, you've got some questions. They're all right here. Look at them all. Some are easy, some are weird. Try them out.